Poisson distribution as a model. To use the Poisson distribution as a model, we need a context where the data is discrete and where the mean and the variance in reality are similar. So if we have experimental data, the mean of that data and the variance of that data need to be similar. They don't need to be identical to each other, but they need to be similar. So starting with some experimental data, we calculate the mean and variance for it, and if they're similar, then the data fits a Poisson model. To use a Poisson model, events must occur randomly, so there must be no pattern in the way events occur. So for example, modeling the flow of cars from some traffic lights isn't quite random if the traffic lights are on a timer. Events must occur independently of each other. So trying to model the number of customers queued at a supermarket checkout with a Poisson distribution may not be suitable because customers who shop in groups are not queuing independently of each other. And the mean rate, the value of lambda, needs to remain constant. So for example, if the number of vehicles flowing on a particular road which is not congested at 2 AM in the morning will be different to the mean rate for 2 PM in the afternoon. In this example, the number of cars passing a point on a road was recorded in 10 intervals of 5 minutes each. There are 10 intervals, so we have 10 data values here. There's a claim here that the Poisson distribution is suitable to model this flow of traffic. So if we calculate the mean and the variance for this data, and if they are similar, then we can say that perhaps the Poisson distribution is a suitable model. So putting this sample of data into the calculator gives a mean of 5.7 and a standard deviation of about 2.4, and the variance, if I square this value, 5.79. The mean and the variance are similar, so the Poisson distribution could be a good model. A new example, an IT room has 5 computer terminals. Quite often, all 5 are in use. X is a discrete random variable representing the number of computers that are in use. The probability that X is greater than 5 from a Poisson distribution is significant. So we cannot use the Poisson distribution to model this context. The Poisson distribution has no upper limit. So in a Poisson distribution, you can calculate the probability that X equals 6, 7, 8, and so on, even though in reality there are only 5 computers available. But because all 5 are quite often in use, the Poisson distribution will give a significant probability that more than 5 are in use, which doesn't make sense in the context because we're limited to 5. Modifying the problem slightly, so we still have the 5 computers, but this time all 5 are hardly ever in use. Again, the number of terminals which are in use could be 0, 1, 2, 3, 4, 5, although the probability that all 5 are in use is very small. So this time we can use a Poisson distribution to model this situation. Even though the Poisson distribution has no upper limit, 5 are hardly ever all in use, so the probability that X is greater than 5 will be really small. So the Poisson distribution is a suitable model if events occur randomly events occur independently of each other, and we're looking at single, random, independent events. You cannot have two events that happen simultaneously. Events must occur singly. And the mean rate, lambda, must remain constant. So the mean number of events in a given time interval is proportional to the size of the interval.